Have you ever wondered why some materials cool down so differently than others, especially when they get really cold? It turns out that the way substances store and releases heat at extremely low temperatures holds a fascinating secret, one that classical physics simply cannot fully grasp. Classical physics cannot fully explain specific heat anomalies, especially at low temperatures, because its fundamental assumptions about energy distribution within materials break down at the quantum level. It predicts that specific heat should remain constant regardless of temperature, which directly contradicts experimental observations in the cold. The core reason for this discrepancy lies in how classical physics views energy. Classical mechanics assumes that atoms in a solid can vibrate at any energy level, continuously absorbing and releasing heat. This idea is encapsulated in the equipartition theorem, which states that each vibrational degree of freedom in a material should contribute a fixed amount to its specific heat. According to this classical model, a solid's specific heat capacity should be relatively constant across all temperatures, famously predicted by the Dulong-Petty law. However, experiments consistently show that as you cool materials down, their specific heat doesn't stay constant. Instead, it sharply decreases, eventually approaching zero as the temperature nears absolute zero. This dramatic drop is the specific heat anomaly, and it puzzled scientists for a long time. Understanding this anomaly requires a jump into the quantum world. Unlike classical physics, quantum mechanics reveals that energy, particularly vibrational energy within a solid's atomic lattice, is not continuous but comes in discrete packets, or quanta. Imagine a tiny ladder where atoms can only sit on specific rungs, not in between. These energy packets are often called phonons, which are the quantized units of vibrational energy. At room temperature, there is enough thermal energy to excite many of these phonon modes, making the material behave somewhat classically. However, as the temperature drops, the available thermal energy also decreases. Soon, there isn't enough energy to excite the higher energy phonons. Only a few low-energy phonon modes remain as active, meaning the material cannot store or releases as much heat. This reduction in active energy modes directly leads to the observed decrease in specific heat capacity at low temperatures. Pioneers like Albert Einstein and Debye developed quantum models that accurately predict this behavior, fundamentally shifting our understanding. This quantum understanding has profound practical implications for material science and engineering. For example, it is crucial for scientists designing components for cryogenic systems, such as superconducting magnets or quantum computers that operate at temperatures close to absolute zero. Knowing how materials behave when their specific heat changes so dramatically allows for the precise selection and engineering of substances that can withstand extreme conditions or perform specific functions efficiently. It helps in predicting thermal stability, managing heat dissipation, and optimizing performance in quantum technologies where thermal noise is a critical factor. The concept of phonons, those quantized lattice vibrations, is a key insider detail here. Each phonon mode requires a minimum amount of energy to be excited, akin to needing a certain voltage to turn on a light bulb. Below a certain temperature, that minimum energy simply isn't available from the thermal environment. This phenomenon highlights a fundamental quantum limit, where the classical approximations, which work so well for macroscopic objects, completely break down. It is a powerful reminder that our universe operates on quantum rules at its most fundamental level, guiding how even seemingly simple properties like heat capacity behave. Ultimately, the inability of classical physics to explain specific heat anomalies underscores the necessity of quantum mechanics for a complete picture of our physical world. By embracing the idea of quantized energy, we gain a more accurate and predictive framework for understanding how materials interact with heat, especially in extreme conditions. This deeper insight not only resolved a long-standing scientific puzzle but also paved the way for developing advanced materials and technologies that relying on precise thermal control, from cutting-edge electronics to the future of quantum computing.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.